Okay, well, good morning or good afternoon, depending on what time zone you're in. I'm Bruce Hurlmeyer. I'm work at Zero Zone. I am the Director of Regulatory Compliance and Refrigeration Technology at Zero Zone. Been in refrigeration about 40 years now. So today's presentation have a number of different items we're going to talk about. More of a general overview, sort of a comfort setting if you haven't had an opportunity to use CO2 systems. I think CO2 systems for just about everybody it will be in your future. Definitely an opportunity and a choice for refrigeration systems as the years go by. So we'll do sort of an overview, talk a little bit about CO2 as a refrigerant, some of the properties, some of the reasons people have adopted CO2, maybe some reasons why people have been a little slow to adopt it. Spend a little time on safety. Zero Zone, we always talk about safety when we do a presentation, a few slides. Have a slide on startup, how to be successful there. Talk a little bit about the types of CO2 systems, some of the energy efficiency improvements that are available, ways you can kind of dress up your CO2 system and improve your energy consumption, and then talk a little bit about defrost, primarily hot gas defrost. So moving ahead, CO2, if you haven't heard about CO2, and not sure if anyone hasn't heard about it yet, but it's really an environmentally exceptional refrigerant, right? There's no attack on the ozone layer compared to, say, 404, that's around 4,000 GWP, CO2 is 1. And depending on your application and the ambient air temperatures you operate in, you can definitely have some reduction in overall energy consumption with that. No phase out potential, right? The air we're breathing right now has a small content of CO2 in it, so CO2 typically isn't considered a refrigerant, as a refrigerant isn't considered a pollutant with it. So we really don't expect to see any legislation going after it, trying to remove it as a useful gas in our systems, nor do we expect it to all of a sudden wind up with high taxes on it. Refrigerant itself, on a per pound price, relatively cheap compared to some of the other refrigerants you might be buying today, 404, 448, maybe some old stores R22, a little lower cost with that. And it has favorable properties. CO2 as a heat transfer solution, or heat, heat transfer, I guess, solution is very good. It transfers heat well, high density, can improve evaporator design, improve condenser design as well. So it's really a good refrigerant. Had been in use years and years ago. I think really the only thing that got added at the time was this higher system pressures. As the new chemical refrigerants came on board, they were designed to kind of avoid that higher pressure, and people gravitated away from CO2. Other reasons people haven't just jumped on the CO2 bandwagon is the equipment costs a little bit more. Um, with the higher pressure, equipment's a little bit thicker, a little bit bigger, has to restrain that pressure and operate at it. So equipment costs tend to be higher. Expansion valves need to be electronic. For some people, that's a non-issue. They've been using expansion valves for 20 years. So buying fixtures with an electronic expansion valve, they don't see a price difference with it. Others who have been using mechanical valves, they would see some price increase to get the expansion valve and the associated controls. But by and large, electronic expansion valves have been in the industry, like I say, at least 20 years. A proven device, right? So nothing to be afraid of with that. Have some concerns. We'll talk about safety in a little bit. Um, you want to make sure you're not trapping liquid, and you really don't want to trap any refrigerant as a liquid between pipes. But CO2, the pressure is going to rise a little bit more, so you want to watch out for that. Cold liquid CO2, um, if you have it sitting on your desk, it's not going to be a liquid. It's going to be a solid. A lot of us may have some experience with solid CO2, be called dry ice, right? And we buy that dry ice if we want to keep something really cold for a long time, if we're traveling or shipping something. Temperature dry ice, right around minus 100. So again, temperature of other refrigerants as a liquid, maybe -50, -60, -40. Again, cold. CO2 just a little bit more intense with that. Then interesting part, refrigerant CO2 is an asphyxiant, like all refrigerants are, but also a narcotic. Can leave you a little bit confused as you start getting higher concentrations of that in your bloodstream. So back to why people have adopted CO2 and continue to adopt CO2. Good heat recovery. So there's an opportunity, again, the properties of refrigerant help with that. Discharge temperatures on a CO2 are relatively high. And if you're in transcritical mode, that CO2 temperature gas is always at a higher temperature as it moves through that gas cooler before it gets to the exit. So you can actually extract a little more heat out of a CO2 system than you can with other systems. Again, that costs maybe $3 per pound to $20 per pound for other refrigerants or possibly higher. You get into some smaller copper lines. CO2 as a refrigerant, we don't need to circulate as much of it to do the cooling work as we would with other refrigerants. So you can wind up with potentially lower installation costs. The one thing though with CO2, it is higher pressure. The copper lines are going to be thicker. So if you get into the extra high pressure copper, pick one of those pieces of copper up and compare it to something else, you definitely know there's more copper in there. So you do have to watch that. You may wind up having a smaller copper line, but maybe a similar cost on it because it's a thicker wall. And then you get into the energy, and energy on a CO2 system can be less than a traditional HFC type system. But the design is important, right? You need to take into account the system you're working on, looking at what are your lowest loads, what are your highest loads, what kind of load profile you have, making selections on the compressors that are appropriate for that. So you have the proper staging. You're not bouncing compressors on and off all day. Even where you might mount, say, the gas cooler, if it's an outdoor gas cooler, you want to make sure you mount it where it can get fresh air. You don't want to set it next to the side of another building or a wall on the roof where it's choked for air. If you have a few different gas coolers running, you don't want them all sitting next to each other where they're starved for air. They can't get air between the center of them. So some of the things you want to do to make sure you get the most out of your system. We'll talk about in warmer climates some additional components that can be added to the system to help improve its energy efficiency. And a lot of times when you are in a warmer geographic southern part of the states, you are going to be adding some of the additional components, adds a little complexity to the system. Some of the other refrigerants that exist out there today, may be familiar with, propane exists, could be another choice for certain applications. Generally in the commercial world, propane is going to be a relatively small self-contained system. It won't be multiplexed. It won't be connected to a condenser. Depending on the equipment, it's not going to be a huge grocery store. There'll be individual units filled with propane. A2L refrigerants, new refrigerants hitting the marketplace, starting to get into installed applications. Different refrigerants there. Less flammable than propane, really hard to ignite it, but they do come with some additional safety concerns because it's flammable. You got to take care of a leak, make sure you get the gas exhausted with it. So that exists. These systems fundamentally would look very similar to what you're used to, 448 or 404A in terms of compressor sizes, heat exchangers, those types of things. Then we get down to the A1 refrigerants. Again, two refrigerants we're used to using. They'll be available in the repair market for repairing systems and things like that. But in the next few years, you will not be able to build a new system with 448 or 404. You're kind of left with the primary one, although there's a couple other choices, really being that 744, which would be CO2 refrigerant there as it moves ahead. So a couple different choices. 744 in a lot of cases will be the one people will be settling in on. So how's the the changeover been going over the years? This is some green chill data on it. And when you look through the numbers, you don't really see a big tipping point where the world, in the United States at least, has transitioned all to CO2. A lot of people are still using the traditional HFC refrigerants, that type of thing, going to distributed racks. Although we in our company are starting to see that tipping point this year. So going from a moderate supply of CO2 systems, now we're getting closer maybe to 50% of the systems we supply are CO2. I think customers are starting to see rules aren't going to be changing. 404, 448 is going away as they look at their choices, which refrigerants they have, what equipment's going to look like, serviceability, length of the refrigerant available in the marketplace, all those things. They're starting to make that push to CO2 where we're starting to see that grow. I think when we see next year's data, we will see that teeter-totter starting to push into CO2 systems. Safety. Talk about safety. Some folks out there may be concerned or shy away from CO2 because it has a higher pressure on it. But it's really about respect. All the refrigerants we use as an industry, I should say all the ones commercially, industrially, basically, they all present safety hazards. They're all working pressurized vessels, pressurized pipes. Those pressures are dangerous, right? If there can be accidents, people can get injured. So it's not a lot different. CO2 isn't like, wow, you got this new risk associated with it. Not really. Maybe a little more intensity in the risk, but really the risk is there. You should have been doing good, using good practice as you've been working in your systems, and you just apply that to CO2. So again, all refrigeration gases can be fatal. If you break a line, fill up a room, it's not going to turn out well for you. It'll displace the oxygen. Most of the gases, or say most of the refrigerant gases, including CO2, are denser than air, so they collect near the floor. Something to keep in mind, if you have a refrigerant leak, refrigerant as it comes out of the bottle virgin doesn't have any odor. Once it's in a system, you wind up having refrigerant oil, so you may see a cloud of mist, and you may smell it. You're not really smelling the refrigerant, you're smelling the gas. One of the things with all of these, they're non-toxic. If that's occurring, you want to get the ventilation on. You want to get out to the open area. Same thing with CO2. Keep in mind, because what happens if you would happen to pass out, you're probably going to land on the floor. Where's the density of refrigerant higher? On the floor. As a side note, if you happen to be in a situation where you find a coworker that is on the floor in a machine room or something like that, your first step is not to go over and find out what's wrong with him. If it is a situation, you have a refrigerant leak, a high density, there's a chance you'll pass out and wind up next to him. In that situation, you want to make sure you get your ventilation, get your doors open, get the air moving before you enter the space. Again, you don't want to have two people down on the floor. So anyhow, CO2 not only is an asphyxiant, but it acts as a narcotic. So as you start building up CO2 in your body, you may have difficulty reasoning. So again, it gets into when you have a leak, you're not there to start solving the leak. You're there to get the ventilation going on so that you can work in the area without passing out, right? It's all about just ventilation, getting outside, how to clear yourself of any challenges with that. Other thing, if you're not smelling any oil spraying around the room, CO2, unique as a refrigerant, as a gas, as it gets into our blood level, it displaces oxygen. We start breathing faster to get that oxygen level up, right? Run down the street, you've exercised somewhere in your life, you start breathing faster. It's trying to get more oxygen in your system. So as a worker, again, pretty basic stuff, things you got to pay attention with. You start breathing fast and you haven't been doing anything. You didn't carry a bottle of refrigerant up the stairs. You're not doing a lot of work. CO2, it's time to find fresh air. Really simple, basic things to do. Other things you get into is personal protection methods. And again, none of these are new. None of these are like, well, it's CO2, you got to have personal protection. Again, all the refrigerants, you should be wearing that, right? Working on a CO2 system, body position. Should you be leaning over, looking down at your face on the top of a valve you're taking apart? Do you want it in front of your chest? Nope. You want to try to start working to the side of your body. Same with any refrigerant. If you're taking something apart, you want to use one wrench or two wrenches. You want to use two wrenches. One as a backup to hold it in position so you're not stressing the pipe or the connection. The second one to pull it off. Again, safety glasses, face shield, long sleeves, gloves, always important to have on. Surprising when I get out to job sites, rarely see safety glasses. You know, if you're out there with your techs and they don't have safety glasses on, they have one pair of eyes. You lose one, it will not grow back. You want to encourage everybody getting out of the truck. First thing that comes out, after you're out of the truck, it's a pair of safety glasses. Get them on. Um, Closing off lines, you need to be careful when closing lines working on CO2 systems. Again, know what you're doing with the system. We will provide piping drawings that show you a schematic of what's connected, where the valves are. I believe all of our competitors be glad to provide that same drawing for that system. So before you go in and start closing valves, you want to realize what are you isolating? Can there be a pressure buildup with that? Good to do with all systems. Lower pressure systems not as critical. CO2 will build a higher pressure. It is important to know your system, know what you're doing with it. Interesting thing with CO2, drop its pressure down, you get down to atmospheric pressure, all that liquid is going to turn into dry ice. Might be flaky, look like snow. If you're from the north, you know what snow looks like. But it can create dry ice plugs. Again, you need to be careful when you get those out. You don't want to start heating things where something that's really cold and you put a heat gun or a torch to it. You stress the components and might rupture that. Last thing on that is just CO2 has a lot of safety valves on them. Depending on how well startup goes or how well it doesn't go, you may have a safety relief valve release. If you're servicing a system, you may be out there because something's broken, which might cause a safety valve to release. They can be loud. If you've never heard a safety valve release off, they have sort of a loud screeching sound to them. You want to watch where your body is. You don't want to be standing next to a safety valve outlet. You don't want to be standing there and put your hand on a safety valve outlet. You know, it could turn out bad if that unluckily have a release on it. Other thing is if you're a jumpy person and you never heard one go off, you might jump back. If you jump back and you're working on a rack, all these racks, a lot of pipes, steel work on it, you might wrap your head on something. So again, you got to be careful as you're working on the system to know what's around you, right? Respect the work you're doing. Comes the startup. With startup, again, CO2 isn't, I guess what I'd say, extremely unique as it comes to starting up a refrigeration system. What it really though comes down to is you can't cut corners with CO2 systems and expect really good outcomes. A lot of the systems that get put in today, the contractors are able to cut corners. They might be, all right, we got her going. Yeah, there's oil in the compressors. Let's turn her on and see what happens. And we'll fix and repair as we go. If we need to, we'll turn the system off for a day or two if it's something big, and we'll work on that. Not so much with CO2. A lot of CO2 systems, again, it depends what you're purchasing, are designed that once they've been charged and operated with CO2, they need to run 24/7. Could be down for a few hours of maintenance, but they're not going to be shut it off tonight and come back tomorrow systems. So how do you get around that? Following good practices. When you're getting ready to start up a system, very important to check the operation of the sensors and check their calibration. Make sure they're reading correctly so that you can, if you're reading a pressure, it is the correct pressure. The software is going to be making decisions on what it's reading, what the sensors are reporting. It's important that they're all there, they calibrate, and they function, and the software sees it. Other thing you want to make sure is you want to make sure the components are functional. You know, you want to make sure, yep, I went up on the roof, and when we forced the fans on, the condenser fans turned. And we want to look at it. Oh yeah, they're turning in the right direction. Yours is actually going through the coil. If you have If you have an adiabatic gas cooler and it's hot, so you're going to be having water running, you kind of want to make sure somebody ran water through those pipes and flushed them, so you don't wind up with the first time you turn it on, you get a slug of dirt and you plug all your strainers. You have to look at that. Verify your compressors start, they run in the right direction. Verify the fans and the evaporators come on and run. All those things, the system needs to be ready to go. Another thing you want to do with that is you want to coordinate with the other trades working on the job site. Once you start your system up, get it going, you got your CO2 in it, you don't want to find out that, oh, the electrician isn't finished with the transformer, it's going to be down for 2 days. Or, the parking lot's going to be down, you're not going to be able to get to the site because they're going to close it to do the parking lot, or whatever else might happen where somebody else in another trade, they've got a schedule, they've got plans, and you just don't know what it is, and all of a sudden you're down and you can't operate. Not so good. Again, with many of the systems, once the system is charged with refrigerant, it's got to go. If you shut the system down and it's the summertime and it's warm, and you haven't invested in other design options, you're going to most likely lose some refrigerant with it. But maybe not. There's some other options that exist out in the marketplace right now. Used our company has sold them with systems. One, 90 bar design systems. All the evaporators are available. We have our display cases have 90 bar coils. You can buy coils for your walk-in 90 bar design. Select the correct components, 90 bar design. System can shut down for days typically, and you'll never lose any refrigerant because of a high pressure in the system. They're designed for a higher pressure with that. Another option to go with is the CO2 condensing units. They're typically connected to the receiver flash tank. They have a small compressor system, maybe 448, some other refrigerant on it, plate heat exchanger. When that turns on, it just keeps that flash tank cold. You do have to make sure they work. I was at a job site, went there, and we had provided the system with CO2 little condensing units to hold the charge down. Contractor was talking about lost a lot of refrigerant. Site, I said, well, okay, what happened? The condensing unit not work? He said, no, when they had the power outage, right, and I think it was a trade shut off the power for a while. Turned out the standby generators did not have large enough gas lines. So when they came on, they couldn't run up full power, shut down. So even though I had the equipment, again, not paying attention, walking through verification, wasn't able to operate. Somebody was cutting corners on the startup being prepared with that job. So it is successful startup. Don't cut corners. Pay attention to your checklist. Make sure you have a good system. So again, we're not going into great detail here on systems, just a note on the types of systems that exist out there. You have the subcritical system, and when we say that system is only going to run in subcritical mode, which means it's going to be condensing below 87.9 degrees. So it has to have a pretty cold condensing medium to stay with that. A lot of instances that'll be a cascade system. There will be another refrigerant system running on the site, and part of that refrigeration system will be a cascade condenser. So if that's a 448 system, one side of the condenser is an evaporator running 448 refrigerant, typically about a 20-degree saturated suction on it. The other side is going to have CO2 hot gas coming from the compressors. And that'll usually be temperate, so it's not as hot as it comes right out of the compressor, but it might be around 100 degrees. It'll condense that down into a liquid, so it's able to feed the expansion valves. We also do have customers that purchase equipment and they have chilled water systems. This tends to be more in the industrial market, and they'll have a supply of chilled water and they'll want a subcritical system because they have cold water. They have 65-degree water. It's going to be able to stay cold all the time. When you're working with a subcritical system, a lot of times the design pressure of the components in the system are going to be 650 psi. To maintain that, again, if you haven't invested in a little CO2 condensing unit, you're going to need to have that cascade system running just about 24/7. Again, it could be down for a few hours, but you need to get it up and running. You can't, in a cascade system, get the CO2 system up and running, then decide we're going to turn off that 448 system for a day or two. Isn't going to turn out. You're going to lose some refrigerant with that. Transcritical, more likely the systems you see in the marketplace, customers we have as well. There they operate critical pressures. Typically, again, when the condensing temperature is over 80, round numbers 88 degrees, you are in transcritical. In transcritical mode, you do not condense. On the outlet of and we're not going to call it a condenser, we're going to call it a gas cooler. If you had a pipe coming out of there, put a sight glass in it, and looked in the side of the sight glass, you would see more of a fog. You wouldn't see a liquid and you wouldn't see a vapor, kind of a fog. You would not see any liquid in the bottom of the pipe. If you took your flashlight, looked down that sight glass, looked in the bottom of the pipe, you wouldn't see any liquid. Maybe a little oil, no liquid CO2. You drop down below that 88 degrees, gets a little bit colder outside, now it's 80 degrees. Take your flashlight, you will see liquid CO2 running in the bottom of the pipe. So that's the transcritical. Unique to CO2, we don't see it in the other refrigerants we use today. High side pressures could operate above 1100 psi. On a hot summer day, you might see discharge pressures at your compressor as high as 1500 with that. Again, subcritical always is going to be subcritical. Won't function if it gets warmer. Cascade condenser starts warming up. Will not function as doing any cooling on the CO2 side. Transcritical, though, will. Transcritical systems are designed to operate transcritically on a hot day, but as the day cools off, different season, colder at night, they will slide down and they will begin to operate in a subcritical mode, and they will be condensing liquid. So we look at the systems and we talk about, gee, we got that energy penalty. CO2 gets to be a higher cost to run, particularly in the summertime, not as efficient as some of the other refrigerants. What we're really seeing with CO2 is it generates a lot of flash gas. When you get into transcritical mode, you wind up with flash gas. This is a pressure enthalpy diagram back when I started in the world of refrigeration. As an application engineer, we had pads of these on our desk. We would design a full refrigeration system using a pressure enthalpy diagram to keep track of what was going on. It kind of went out of favor as computers came along. You didn't need to think too hard about it. Get back to CO2, systems a little more complex. Mapping them out in a pressure enthalpy diagram is important. Have different things going on. Pressures on the left-hand side, low pressure at the bottom, going up to a higher pressure on the top. Energy lower on the left-hand side, higher energy on the right-hand side. For the section that we're going to be talking about, we're going to be interested in the left side of this dome represents liquid. The right side represents vapor. What's in between represents a mix. And graphically, the position of that line tells us how much is vapor and how much is liquid as a percent weight. Up at the top of the dome, CP, it's our critical point, again, about 88 degrees. So this diagram, as it's drawn, says, okay, this system is running in transcritical mode. If I'm going to be subcritical, I have to cross these lines. I have to do condensing inside here. Transcritical mode isn't going to condense. It'll start producing liquid as we drop its pressure. But what we're interested in as we talk about kind of big picture efficiency, it's all about flash gas. Flash gas isn't usable for doing refrigeration. Flash gas, when it's generated, refrigeration systems, they all generate some flash gas, winds up eventually going back to the compressor without doing any work, gets recompressed, gets cooled, turns into flash gas, so it's kind of a waste. So when we look at systems and look at how do we improve our efficiency or why is our efficiency dropping, it's a lot about flash gas, how much flash gas is being made. So an example, subcritical CO2 systems, you have a vapor on the side, a compressor number one, condenser, So as that gas gets cooled, it will turn to a liquid. If you have a sight glass on the outside, you will be seeing mostly liquid coming out of there. Goes through an expansion valve, turns into a liquid and a vapor. In a normal system, and this CO2, when it's subcritical, you're generating a little flash gas. Nobody really talks about it because it just goes off with the evaporator, goes mixes with the liquid as it gets boiled away in evaporator, and eventually shows up as a gas going into the compressor. So that's why you'd never heard much about it. Well, let's say in a 448 system. You start seeing it now when we talk CO2. Go to transcritical. Now I'm not able to cool as much. It's a little bit hotter outside. So I got a compressor, got a condenser. I've got a high pressure expansion valve. It's going to drop the pressure in it. It's going to dump the liquid into a tank. Liquid will drop to the bottom of the tank. Vapor will go off to the other side. That liquid, when it goes through the expansion valve, again, you're going to have a little segment of flash gas, but in totality, you have this longer line of flash gas. So you're generating more gas that isn't useful. So that's where it starts nibbling away at the efficiency of a CO2 system. This gas, this flash gas, is taking up space. The compressor needs energy to compress it, so it becomes a waste. So as we look at making things run more energy efficiently, it's all about processing flash gas as cheap as possible. How can you spend the least amount of electricity to get the flash gas shot back up to the condenser and making a loop through the system with that? When we look at weather data, or say when you look at system design and you're starting to make a decision of what's my energy consumption going to be, can I run it in this area, this location, you really want to get out and take a look at weather data tables to see how many hours do you have at which temperature levels. All right, so this is Phoenix, and I think we got the slide. Emerson Technologies, although now called Copeland, had the information available. And really with that, out of the 8,700 hours that are displayed on here, only 3,275 would typically have the system running in transcritical mode, or about 37% of the time. So you don't want to think, boy, I'm in Phoenix, it's going to always be transcritical. Not so. A portion of the day, a little over a third of the time, will be spent in transcritical, but not the other one. So you want to run the numbers. What's my energy consumption going to be with that versus the benefits of CO2 as a low-cost refrigerant that's not going to go away type of system. And also on these cooler days, the ability to be gaining energy efficiency over other types of systems. Get to the northern climates, Minnesota, and I'm out of Milwaukee. We have a plant in Minnesota. They're, as expected, a little bit different. Out of the 8,700 hours, only 663 hours, 7-8% of it runs in a transcritical mode. Otherwise, you're going to be running much more like a traditional system. Very limited higher energy days when you're running up in the transcritical mode. So again, it comes down to as you're making these decisions, wanting to work with the equipment providers, right? We'll do that. Our competitors, everybody will do that. Help working with you and give you an idea what your estimated energy costs will be for the location you're in with that. And you have, so as we look at it, a lot of times system design changes as you work through them. It's all about modifying the flow path to get gas moving to the highest suction compressors, right? You want to have the lowest pressure differential. A low pressure differential means less energy consumption by the motor. So that's one of the big things. We'll see a couple items to do that. The other way you do it is by trying to improve the amount of energy each pound of refrigerant can absorb when it's circulated. So you're trying to get that refrigerant colder before it goes into the evaporators, right? Then I don't have to circulate as much. My compressors don't run as fast. And then this is controlling the energy consumption of the rack. But then, okay, I'm putting that energy in. How can I recover it? How can I use it for something else? It's looking at the opportunity of a transcritical system for heat recovery, right? What other things do I need to do to get some heat out of it? And even though it's transcritical and subcritical mode, again, you can still be scavenging heat out of the systems. You can offset any heating costs in, the Minnesota northern climates with that. One of the ways, very common in the industry to reduce the pressure differential the compressors work at, is lowering the gas cooler condensing temperature. Biggest method there is the adiabatic condenser gas cooler. And I think when I was looking back at presentations, NESRC had a presentation a couple of weeks ago. You can look at that. Using an adiabatic cooler. With an adiabatic cooler, think a swamp cooler if you're from the south or southwest. If you take warm, dry air, run it through a wet pad, the air coming out will be moist. It'll be wet from going through a wet towel, but it'll also be cooler. Depending on your conditions, the ambient temperature, elevation, wet bulb, dry bulb, you could possibly see a 20-degree improvement. So instead of switching into transcritical when it's 80 degrees outside, right, starting to burn a little more energy, it won't happen until you get up to 100 degrees. It gives you an improvement there, just to save some energy with it. And again, you have to go back and look at weather data to understand how much you can save and what time of the year. Evaporators, trying to increase the evaporating temperature of the evaporators. You can use a liquid overfeed using all the surface of the evaporator. There's some systems out there using a wet return direct expansion. So it's still an expansion valve, but you're not dumping back a ton of refrigerant to flood the compressors out. Then there's some additional, as we get to additional devices that can be used to help move CO2 vapor around the system. A couple different manufacturers of ejectors may take gas from the medium temperature evaporators, push that back up into the flash tank, that type of thing, be able to move it around the system. Pressure exchangers, do some work with the flash gas. Again, a couple of weeks ago, there was a presentation on that. From that manufacturer, you can go back and look at the website. Parallel compressors, we do a little work with parallel compressors on that. Has the opportunity, the gas that's getting generated as it goes into the flash tank, that first bunch of flash gas can get compressed with another compressor operating at a higher suction pressure. Might have a higher suction pressure, maybe 100 pounds. Can make a big difference in energy consumption. We'll see that in a couple of slides. Tend not to see a lot of these right now. A lot of additives, even though they're there, we share customers' opportunity. Technicians are still learning CO2 systems. So in a lot of cases, they're looking for a basic system. Customer says, yeah, my guys are new. They're just going with it. If I have less items to control, less PIDs moving around, that type of thing, I want to stay with a simpler system. So while we've sold parallel systems and it's not the most prominent. Even in some of the warmer climates, people opt for very, say, basic systems with that. Other improvements with that, liquid to suction heat exchangers. You have the opportunity, the cold suction gas can cool your liquid. Having you have to circulate less through your system makes it more efficient. Also gives you a chance to warm up that suction gas. CO2 takes a lot of energy to get it to boil, so you like to have some warm suction gas to make sure you don't get oil, in your compressors that minimize floodback as well. Some systems you can also use a mechanical subcooler on the outlet of the gas cooler. With that might be tied to a different refrigeration system, possibly tie it to the building's air conditioning system. Air conditioning systems, they've been, their designs have been getting updated to be constantly more energy efficient. A building air conditioning system has a much higher EER value, energy efficiency ratio, compared to a CO2 refrigeration system. So there's some opportunity to do some additional cooling with a more efficient system before you turn it to start feeding that CO2 through the system. And again, this is the heat exchanger that gas is hotter, particularly in transcritical mode. And when you're in transcritical mode, that temperature differential is always going to be higher compared to a system that just has a heat exchanger between something that's condensing. So depending what you're operating, you may do that. We've had one customer that opted to run in transcritical mode, kind of working as a heat pump. He had another place for some heating and wanted to stay transcritical to be able to do that and scavenge that heat. So a little bit about energy. We talked about some of those different devices. How do those have an opportunity to save some energy? We had a customer of all places, Minnesota, ice rink in Minnesota, and it was owned by a municipality. They were asking for different ways to reduce the energy consumption. It was taking an existing rink, removing I don't know if it's 502, 22 system, putting in a CO2 system on it. So we ran some different scenarios on it. We said, all right, if you buy your lowest cost simplistic system, it's going to have just a dry gas cooler outside, and flash gas just goes to the compressor, have an ER ratio on it. Going in, if you said, all right, I'm going to add a parallel compressor to it, so I'm going to process some of that flash gas, not run it right to the medium temp compressors, save a little more energy, right? Energy efficiency, bigger's better. If I do something different, I'm going to run adiabatic instead of flash gas bypass. I'm going to gain some efficiency with that. I'm always going to be cooling. You see that step here, right? That's where we turn on the water a little bit. And then the last one, you could turn them both on. Turns out the customer decided he wanted both. So both of those systems are up and running there. Our director of engineering, Adam Szelski, a few years ago did a ASHRAE Minnesota presentation for them and went through, and as part of that, we went out and estimated what the EER ratio was of the system as it was operating, as the ice rink was operating. And we had, some limitations on how hot it gets in Minnesota. So we looked at two different dates, 70-degree day and an 85-degree day. And we had watt meters on, so we know the power consumption. And then use the pump curves to look at what the flow rates were, and then looked at the temperature in and out of the pumps temperature in to the pump and out of the heat exchanger to know what the system capacity was. So with that, we're able to do some calculations. You take a close look at the numbers. A couple of them look a little like, that's a little weird. If you've ever gathered information in the field and analyzed it, be really surprising if you didn't get a couple numbers that, they look a little weird. It's part of the excitement of field data gathering. But with a 70-degree day, our ER started out at 6.5. When we opted to use just a dry gas cooler parallel compression, got up to 8.8. So we saved about 35% more efficient there, improved our EER. Opted to go the other way and said, let's put on the adiabatic cooler with flash gas bypass. Not a big savings. That's at 70 degrees. If you're peeking ahead at the other column, you'll see a little better savings there when it's hotter out. A lot of the adiabatics turn off between 60 and 70 degrees because you're not saving enough energy to pay the water bill or the sewage bill on the water type thing with that. When we went to both of them together, and these are where it's a little odd because it actually got lower than just a parallel compressor by itself, got down to 8.5. But again, some opportunity on the cooler days to save energy. On a hotter day, bigger savings are available with that. When we use the parallel compression, 43% improvement. When we had the adiabatic, 41%. And notice, here we talk about how much can the adiabatic cool it down. Well, this 6.9 is a lot like a dry cooler over here. So when I look at it, I'm thinking the air coming off of the adiabatic cooler after it's gone through wet pads might be a little less than 70 degrees on that 85-degree day. So we cooled it probably better than 15 degrees. We saved some energy. And this one is a little more expected where we can gain a little bit more savings running both of them at the same time with it. So again, savings are available, so it's important to work with your suppliers. Where's the equipment going? What are you going to do? What loads, big loads, small loads, how much do they shift? Look at the weather data, and you can come to some solutions that CO2 isn't that big of an energy penalty for you. Maybe not an energy penalty at all, right? Shouldn't be a reason you would shy away from using that as your next refrigerant. So lastly, hot gas defrost, another opportunity to save some energy. You don't have to be plugging in electric heaters with it. Number of systems are out there running with it. Zero Zone uses a high stage discharge gas system. So we're taking our hot gas out of the discharge line. Out of the discharge line in a lower, typical, what you see in grocery stores, 45 bar system. We regulate that gas into a hot gas header. Typically pressures would be about 550, somewhere to 575. But notice the saturated temperature, 40 degrees, 43 degrees. Not real warm when you compare it to ice at 32 or a coil that might be running at minus 20 and you got to get it warmed up. From that hot gas flows through the suction line. This is the controlling pressure. Goes through the coil, returns through a discrete header back to the flash tank receiver. Flash tank receivers, depending on design principles, different people what they pick, it might be around 525, 36 degrees. Again, relatively cold, right, compared to ice. But it is warm enough. You are successful at defrost. We have lots of systems out there. They're defrosting away. You're not having iced coils. They're running 3-4 years type of thing. But what you do find, longer defrosts. If you're used to hot gas defrost and other systems, you might be thinking 15, 20 minutes, boom, I'm out, I'm back in refrigeration. When you're doing this type of system in a 45 bar system, think electric defrost. 45, 50 minutes, maybe timing out, never temperaturing out. Advantage of the system like this, there's no artificial increase in pressure. So that system's just running along. Nothing happens on a discharge side of the compressors when we go into hot gas defrost. Plenty of pressure available. So there's no energy penalty from jacking up one of the compressors to get that back. The coils actually work as condensers, right? Hot gas in, liquid out. Liquid goes back to the receiver, and it has a place to go out to all of our evaporators. We also have other systems you get into. Primarily, we've got a couple stores now that are using 90 bar coil evaporators, so they're going with a 90 bar type defrost system. We've used it more in industrial applications. Industrial applications, they turn things off for a long time. They like higher design pressures. A 90 bar system, 4-pipe system with that. We're going to have a hot gas header pressure, hot gas header again. We're going to regulate that pressure much higher. It's going to regulate at 750, maybe to 800. And from there, that hot gas header is going to feed, it's going to feed the evaporators, go in through the suction line on it, but we're going to control the evaporator pressure at 684, round number. Well, it's not a round number. 55 degrees is a round number. So instead of that pressure being relatively low, 550, 575, we're a little bit higher, and we're getting up to 55 degrees with that. So that'll run in there. We'll keep those evaporators at a higher saturated suction. From there, the gas liquid returns through its own line, goes back to through a discrete header back to that flash tank. These are faster. These are more traditional. When you run these, you're looking at the 10, 15 minute defrost on it. You hit your temperatures. Obviously, you have to have a termination temperature below 55 degrees to hit it, but if you're at 50 degree termination temperature, you're going to hit that and get that to go. And again, using discharge pressure, we're not doing anything with the compressors to artificially raise pressures or anything like that. During defrost, those are truly acting as additional little condensers for us. So with that, hopefully an overview of CO2 systems. If you haven't used them before, thinking, yeah, there's a lot of benefit to a CO2 system. Technology is not that new or unique from any other refrigeration system there. Working with suppliers, you can have a well-functioning, energy-efficient system that You know, a lot of people use the term future proof. That refrigerant will not be going away in 5, 10, 15 years. So with that, we have a few minutes left. Any questions?